Hey, what's up? It's your old pal, Mr. Cook. We're going through this review. Let's see what happens with it. Okay, so now we're at the limits stuff. I think let's go through the first two. And if we got time, we'll do the third one. I don't know. All right, so I don't know how much space I'll have. So I'll probably go through number 5, erase it, and then do number 6. So number 5, now, when you're dealing with limits at infinity or at 0 or any value, you're always encouraged to like plug in or evaluate immediately. Okay, so I like to just kind of like see what happens before I start writing up real formal stuff. So if I were to I know this goes against what we're trying to teach you, but if I were to plug in infinity, plug in a gigantic number, this natural log of a really large number, so natural log of infinity essentially, it also goes to infinity. Okay, so that means that overall this thing just becomes infinity. Okay, and then if I take the natural log of infinity again, guess what? I get infinity. So this is going to become infinity eventually. And same thing here. If I plug in infinity, natural log of infinity goes to infinity. So this part's also going to go to infinity. So do you see what's going to happen? We're going to have to use L'Hopital's rule for this. Okay. So now let's go through the formal process of showing that we can use L'Hopital's rule by getting an indeterminate form. So we take the limit of the top separately from the limit of the bottom. So we do limit as x goes to infinity of the natural log of the natural log of x. We showed that that goes to infinity a little earlier. So we just write that statement, that declarative statement, and we're good to go. And then we need to show that the limit as x goes to infinity of the bottom part as well, natural log of x. That also will go to infinity. So since this is an infinity over infinity form, we make a little statement. Infinity over infinity is an indeterminate form. So we can use L'Hopital's rule. Let's write L''H. Hope you don't mind. It gets the point across. Okay, so there we go. So it's an indeterminate form, so we can't use L'Hopital's rule. We actually can't use L'Hopital's rule unless we get one of these indeterminate forms in some way. So we got the one where it's infinity over infinity. So just be aware of that. Okay, so since I can use L'Hopital's rule, now I'm going to go ahead and use it. So I'm going to say that this is equal to the limit as x goes to infinity of, and then I take the derivative of the top part and the derivative of the bottom part separately. So the derivative of the natural log of x. Well, that's a chain rule problem because it's a function and a function. The derivative of the outermost function, natural log, the derivative of natural log of something is 1 over something. So it's going to be 1 over the natural log of x. And then I've got to, use the chain rule. So now I got to take the derivative of the natural log of x, which would be 1 over x. Okay, there we go. That looks nice. Now let's take the derivative of the bottom. So the derivative of natural log is 1 over x. Do you notice something? We've got a 1 over x in the top and a 1 over x in the bottom. Those will just reduce. So this is going to become the limit as x goes to infinity of 1 over the natural log of x. And as x gets really, really, really big, that natural log of x goes to infinity. And, if we have like a 1 over infinity situation, that basically goes to 0. So 0 would be my limit for this graph, or for this function. Okay, so there we go. After using L'Hopital's rule once, I show that the limit goes to 0, and that's my answer. All right, now we go on to number 6, and that's where it gets a little more challenging, because if you look at the function, the way that it's set up, we've got a function of x raised to another function of x. And if you remember back to logarithmic differentiation, that's like a dead giveaway as to what you're supposed to do here. So first and foremost, we're going to make an assumption. We're going to make the assumption that this is going to be equal to some limit. And since I have a function of x raised to another function of x, what I'm going to do is take the natural log of both sides. And I'm going to do my work over here on the left-hand side. So I get the natural log of the limit as x goes to 1 of, oops, let me make that look more like 1. There we go. Of x raised to the power of 1 over 1 minus x. And then that's supposed to be equal to, since I take the natural log of the left-hand side, I also got to do it on the right-hand side. So the natural log of L. Okay, so there we go. So from my assumption, now I've got this. And the next step is that I'm going to show that since I have the natural log of the limit, it's the same as saying the limit of the natural log. So I'm going to rewrite this as the limit as x goes to 1 of the natural log of this stuff right here. Okay, and that's a nice algebraic step that you can use, that you can write it out. But I think that you can actually like skip it if you need to just get to this point. Okay, so the whole reason that we do the natural log, in this situation, is that we're allowed to separate these two, because we use this rule where if you take the natural log or the log of some exponent, you can rewrite it by adding the exponent power as a multiple out front, or a scalar multiplier of the natural log. So that's what I would do here, and it works for functions as well. So I can move this. Oops, maybe moved a little too far. I can move that exponent power out to the front of the natural log. So here's how I set up all my stuff. I get the limit as x goes to 1, and then it's going to now be 1 over 1 minus x, and then times the natural log of x. And I might even make that look a little bit nicer, honestly, because I can just move that x like up top. So I'd make it look like this: natural log of x over 1 minus x. Okay, so now let's just in our heads, I'll write it down, but you can kind of do this in your head. What happens when we plug in 1? Well, the natural log of 1, is going to be 0, and then 1 minus 1 is going to be 0. So it looks like I'm going to get a 0 over 0 situation. So this is going to be L'Hopital. So I got to do something similar to what I did in number 5, and just show that it's going to be an indeterminate form, and then state that I'm going to use L'Hopital's rule, then use L'Hopital's rule. All right, so let's do that. So now I show my limits, and this is going to be an indeterminate form. Let's use some color on this. So the top part, I write the limit as x goes to 1 of the natural log of x, and that's going to go to 0. And then in the bottom part, the limit as x goes to 1 of 1 minus x, that's also going to go to 0. So 0 over 0 is one of those indeterminate forms. So we can use L'Hopital's rule. All right, and then that's when we do our derivative and reevaluate it. So let's see what we have now. So once we do L'Hopital's rule, so we get the limit as x goes to 1, and then we take the derivative of the top part. So the top part, the natural log, the derivative of the natural log is 1 over x, and then the derivative of the bottom part, 1 minus x, is negative 1. So I can just rewrite that. That's the limit as x goes to 1 of negative 1 over x. And then if I plug in 1, right, I just get a simple value, negative 1 over 1, which is negative 1. But that's not the whole thing, okay? Because remember that when we started this limit off over here, that solves for the natural log of L, okay? So here's the last little part. We know that negative 1 is, our limit, but that's equal to the natural log of the limit that we're seeking. So we just need to solve for L, and the way that we do that is by exponentiating both sides. In other words, raising both of the sides as powers of e. So I get e to the negative first is equal to L, and that's good enough. That's my answer overall. L, the limit, is e to the negative first. Okay, yeah, I think I'll stop here for this one. So we did number 5 and number 6. 7, if you can spot a really easy simplification for this, it's really simple. But other than that, you'd need to do L'Hopital's rule a couple times. I'll show you how to get the really easy answer with it, though. Okay. All right. So let's do number 7 and number 8 in the next video. All right. I hope you enjoyed this one. I'll see you in the next video. Bye bye.